and that pendulums, as we're going to see here, are a good way to help us start talking about waves, because objects in simple harmonic motion, objects that are vibrating, objects that are oscillating back and forth, are ultimately the cause of all wave motion. And so a wave is simply a disturbance in the force that's transmitted progressively from one place to the next with no actual transport of matter. Now, what does that mean? All it means is that we have energy moving through either a vacuum or a medium without actually moving the matter that it's moving through. And we're going to come back to this point. We're going to repeat it about a dozen times today. This idea that matter doesn't actually get moved from its original location, only the energy does. And as we'll see many, many times, we represent our waves with sine waves graphically. It's the easiest way. And we're going to have a couple different types, but our sine waves are a nice, easy way to represent what's going on. Now we have a scientist, Frank Oppenheimer, was the first person to really connect the ideas of simple harmonic motion and wave behavior. And so he was, bored hanging out, letting a pendulum swing back and forth. He connected a pen to the end of it and let it swing back and forth over a piece of paper. Okay, what's that going to draw? It's going to draw a straight line. That's pretty straightforward. But when he took this little machine down there that you see at the bottom right and allowed it to roll the paper out at a constant velocity, he saw that he got a sine wave. And you can see it there on the paper as it's being drawn, how we have this curve and it's going up and down, up and down, up and down. And all that's coming from, there's two things going on. We have the oscillation of the pendulum back and forth, and we have the paper rolling forward through time. And so we have this combination of a change in position and a change in time. And our waves are common. They're all around us. We experience them every single day. We're experiencing them now because you're listening to me. You experience them because we have light shining so that we can see. You're able to click through the notes on your computer because the wireless electromagnetic signal is traveling from the router to your computers, which is why we can access the internet in class without being hardwired. So they're all around us, and there's a variety of different kinds. And we're going to look today actually at waves in springs. We're going to start today. And we're going to look at waves, some kind of straightforward, simple waves, because if we can understand how waves behave in material like springs and like strings, then we can apply those ideas, those concepts to all types of waves, because the behaviors, the properties, the ways that the simplest waves behave is the same way that our light waves, that our electromagnetic radiation traveling through space behaves. It's the same way that the sound that's traveling through the room behaves. And so we can use one type of wave and our knowledge about it to study others. Now, as we work with waves, we're going to want to, as with anything, classify them. And there are a couple ways that we can, and the first is based on whether or not they need a medium to travel through. And a medium is simply matter. Okay, so when we have a medium, let's change the color. There we go. The matter through which the wave travels. So the medium, that term just means the matter through which the wave travels. And it could be air, the spring, it could be a wall, whatever it happens to be. So those types of waves, the waves that have to have some matter to travel through, those are what we call mechanical waves. Sound waves, water waves, seismic waves, the waves that are a result from earthquakes. Those are all mechanical waves. The waves that we're going to look at in springs and strings, those are all mechanical waves because without matter, they don't travel. If you were to go into space and you could somehow survive without a spacesuit and you tried to yell, there wouldn't be any sound. Nothing would come out because there's no air in space to carry forward that energy, that sound energy. The waves that don't need that medium, the waves that can travel through space, are what we call electromagnetic. And our electromagnetic waves, that's the entire electromagnetic spectrum. It's our visible light, it's our X-rays, it's our gamma rays, it's our microwaves. It's everything that's talked about in the electromagnetic spectrum song that if any of you have had a class here, you've probably heard at some point. It's the best song ever. We will listen to it many, many times in this unit. But it's all of those. And those particular waves, our light, our gamma radiation, our X-rays, those can all travel through a vacuum. Those electromagnetic waves are what we call self-propagating. The electric field creates the magnetic field, which creates the electric field, so on and so forth. And we'll talk really, really in depth about those in the next unit. But they travel through everything, and it's the light that we see. Now, it can travel through a medium. It can travel through glass. It can travel through water, things like that. But it doesn't have to have that material in order to travel. Okay? And then, if we look a little more closely at our mechanical waves, we have two types of mechanical waves. We have what are called transverse, and we have longitudinal. And they vary based on the vibrations of the medium. Our electromagnetic waves are all basically transverse, but when we have a medium, we can either have transverse or longitudinal. And so we're going to look at each one of these. And the impact or the thing that determines which it is has to do with direction of medium oscillation. And so with our transverse waves, you can see that the wave here is moving from left to right. Okay? So moving from left to right. And actually, so let's start with what we call a pulse. Okay, this is what we call a pulse. And it's simply a single crest or a single trough. We'll talk about what those are in a moment. But it's just one part of a wave. And so you can see the actual energy in the wave is moving from left to right. What direction is the medium oscillating? What direction is the medium moving? It's moving up, right? So here, our medium starts at equilibrium, and it moves up. And you'll remember we talked about simple harmonic motion and oscillations and displacement from equilibrium. That's what's happening here. The medium is being displaced from equilibrium in the upward direction, and it's the opposite direction, or it's at a 90-degree angle. It's normal to the direction of energy transfer. So it's perpendicular. So we have displacement up and down. We have wave movement at a 90-degree angle. And what happens to the medium after the wave has passed? Where is it? Where is it relative to where it was before? Returns to equilibrium. So the medium isn't displaced indefinitely. It returns back to where it starts from. It returns back to where it starts from. And you can see that here. Okay, so there's our pulse. And then the other type of wave we can have is called a progressive wave. This is a progressive wave. How does this differ from what we just saw? What's different about this from what we just saw? Okay, it's above and below, and it's continuous. Okay, so a progressive wave is continuous. A pulse is just one crest or one trough. A progressive wave is a continuous wave. Okay. Now the other type is a longitudinal wave. And so let's start with a pulsed, what we call compression. Okay. And here, what we should see, what's the direction of the energy of the wave? Okay, left to right. So our energy is moving in this direction. What's the direction of oscillation of the medium? What direction are those little bars oscillating? Are they oscillating up and down or left and right? They're oscillating left and right. All right. So in our longitudinal wave, the medium oscillates in the same plane or in the same direction as the energy is moving. Okay. And with our longitudinal waves, or we sometimes call compressional waves, you'll remember from what we just saw with the transverse waves, the medium moves up and down. We have our crests and our troughs. It moves away from the medium up and away from the medium down. Here we're actually vibrating back and forth, which creates these areas of denser material. And we have areas, these are denser, and we'll come back to these again, but we have denser. And then here, it's less dense. All right, these are what we call compressions and rarefactions. Compressions and rarefactions. Okay, and if we pull out a progressive wave here, one that just keeps going, we can see compression, rarefaction, compression, rarefaction, compression, rarefaction, as it gets squeezed and spread out, squeeze and spread out, squeeze and spread out over time. Okay? Now we'll come back to these in a little bit after we've talked a little bit more about our parts of a wave. And so again here, what we just mentioned, the waves here are moving from left to right, but the direction of displacement of the medium or particle motion is either at a right angle to or in the same plane as that direction of propagation. And direction of propagation just means the direction the energy is moving in the wave. And again, can't stress this enough, when a wave propagates or moves through a medium, there's no net movement of matter. Okay, we saw that on those previous animations. The matter, the medium that the wave is moving through, always ends up back where it started. Okay, it doesn't end up further down the line. It oscillates back and forth and always returns to where it started, just like with our pendulums swinging back and forth. They always end up back at equilibrium. With our springs oscillating up and down, whatever it happens to be, only the energy gets transferred. Only the energy ends up moving from one place to another. So, let's talk about the parts of the wave. Okay, we got a couple different parts that we're going to need to know. Let's use the high parts. And what type of wave is this that we have drawn up here? Transverse. Excellent. This is a transverse wave. The tops of our transverse waves, so here and here, these are called our crests. Like that. Here we go. Here and here, those are our crests. Our crests are in yellow. And then we have the low parts. The low parts are our troughs. There's our trough. There's our trough. Okay? So our troughs are in green. The distance from equilibrium, and equilibrium is that line in the middle there, where if there wasn't any wave, okay, this is our equilibrium. If there was no wave, where would the matter be? That's the equilibrium position. Okay? The distance from that equilibrium position up to the crest is what we call the amplitude. Now, if we look at the amplitude, we have it drawn up here on this left-hand crest, and I just drew it in on the right-hand crest. How does that distance, though, compare to, say, if we drew it down here from that equilibrium position to the trough? It's the same. Okay? And that's another important piece to remember here. The amplitude is the maximum displacement from equilibrium in either direction. It's not just the distance to the crest. It's not just the distance to the trough. It's the distance from equilibrium to the crest or the trough, because that displacement, assuming there's no energy loss, is going to be the same. So another way to write this is, or if we think about this, what is it if we were to consider the distance from the crest to the trough? What is the amplitude relative to that distance? So from the crest to the trough, it's what? What is it, Michael? Other way around. It's half as much, right? So from here to here, that's the distance from the crest to the trough. The amplitude is half that distance.
Oh, I thought you meant like...
The other way around.
Yeah.
Gotcha. Okay. Then you're thinking about it the right way. Okay. So it's half that distance, or if you're thinking about it the other way, twice. Okay, but that distance, positive or negative, it's basically the absolute value of that. Okay. When we talk about the amplitude, when we think about it in terms of sound, we're thinking about the loudness. When we talk about it in terms of light, we're talking about how bright it is. So the brighter the light, the louder the sound, those relate to greater amplitude, because the amplitude of a wave is essentially the energy in the wave. The energy in the wave is actually proportional to the square of the amplitude. Okay, the energy in a wave is proportional to the square of the amplitude, which means that if the amplitude doubles, what does that do? Wow, that is dark. What does that do to the energy? If we double the amplitude, how much does the energy increase by? No. If this number goes up by a factor of 2, how much does this number go up by?
Ben says 4.
Ben is right. More people should listen to Ben. Right? Because it's squared. So if we double the amplitude, it's 2 squared, which means it goes up by a factor of 4. If we increase the amplitude by a factor of 3, the energy goes up by a factor of 9, and so on and so forth. Okay? Good answer, Ben via Michael.
You're welcome.
Now, the other piece that we need to be able to measure is what's called the wavelength. And the wavelength is simply the length of a wave. Pretty straightforward. It can be measured most easily from crest to crest as we have it drawn here, but it's really between any 2 successive points on the wave. And so we can draw it not just from crest to crest. It can also be from trough to trough. Okay, that's the same distance. And you'll notice, so this little thing right there, that is what we call a yes, somebody knows it. Very good. Ben is rocking it today. Okay, that is a Greek letter, lambda. I assume they picked it because it looks somewhat wavelength, but I don't really know for sure. So wavelength is lambda. It can be also, we could measure it from, let's see. Again, doesn't really matter. We can measure it from here to here. All right, those are two successive points. We could measure it from here to here. There's two more successive points. Or from here to here, two more successive points. Those are all equal to the wavelength. It's simply one full crest, one full trough. Okay. Now, those pictures showed us these pieces on transverse waves, but let's talk about them relative to our compressional waves briefly. So, in compressional waves, instead of having crests and troughs, we have compressions and rarefactions. And our compressions are, kind of like the crests. And so if we were to draw a wave, it would look, our transverse wave might look, that is not great, but you get the idea. So our rarefactions are similar to our troughs. In this case, look what's happening to the medium in the rarefaction. It's being spread out, right? It's being spread out. The term rarefied just means it's becoming less dense, and that's what's happening to the medium here. It's becoming less dense because it's being stretched apart. But if it's being stretched apart in one part, what has to happen somewhere else? It's being compressed. It's being squished together, right? The medium doesn't just disappear. It's matter. It can't be created or destroyed, right? So it has to go somewhere. So if we're stretching it out in one part, it has to go somewhere, and it's going to end up being compressed. And so, by popular demand, we call those areas compressions. So instead of crests and troughs, with our longitudinal waves, we have compressions and rarefactions. And we measure wavelengths the same way, though. All right, so here we go from compression to compression, or we could go from trough to trough, or from rarefaction to rarefaction. There's a wavelength. Or we could go from here to here. Here's another wavelength. Okay, so again, any two successive points on the wave. Okay. So and here then also the amplitude of a compressional wave is a measure of the change in the matter. In a transverse wave, it's how far it moves away from equilibrium. And we could do that here. We could measure how far the medium oscillates away. Typically, though, we measure either the change in density or we measure the change in pressure. Because particularly with air, as you're talking, as I'm talking, as you're talking, as we're talking, as that sound wave moves through the air, it's the air molecules that are oscillating back and forth. And as they move together, they get compressed and they become more dense. Denser air has a higher pressure. And so you have areas of higher pressure and areas of lower pressure because less dense air has less pressure. And so what ends up happening is you have changes in air pressure from what's normal. If we just sat here in silence, the air would be at about 1 atmosphere, because that's the typical standard pressure of air at sea level. Maybe a little bit less because we're a little bit above. But as sound waves travel through, that pressure changes. And just like with our compressions, with our crests and our troughs, however much it goes up is also how much it goes down. So if the pressure increases by 0.5 atmospheres in the compression, then it's going to go down by 0.5 atmospheres in the rarefaction. So the difference, that amplitude, is still going to be the same magnitude. Okay? Now, as we continue to describe waves, we can also talk about them in terms of their frequency. And the frequency, again, similar to when we talked about circular motion, is how many times per second something happens. When we talked about circular motion, it was how many times the object traveled in a circle per second. When we're talking about waves, it's the number of vibrations or the number of full waves that occur per second. Okay? And again, it's still measured in hertz, and hertz are cycles per second. When we're talking about waves, the frequency of the wave is also the frequency of the thing that's oscillating to create the vibration. Okay, so if you have a tuning fork that has a frequency of 550 hertz, those tines on the tuning fork oscillate back and forth 550 times every second. If you have an electromagnetic wave, like a radio wave that has a frequency of 960 kilohertz, that means the electrons that are oscillating back and forth in the antenna to create that wave are oscillating back and forth 960,000 times per second. Okay? When you look at your radio dials, when you're changing stations, if you're using AM or FM, those numbers, the 101.1, the 98.7, the whatever it happens to be, those are frequencies. Okay? Those are frequencies in megahertz, so in millions of hertz. Okay? And that specifically is telling you the wavelength of the radio waves that you're receiving at that time. So those aren't just random numbers. When we talk about hertz, again, understand that we use our same use our same metric prefixes. So kilo is thousands, mega is millions, giga is billions. Okay, don't be confused by that. And when we talk about frequency relative to sound, we're talking about pitch. So when you go higher frequency sounds, that's a higher pitch. Lower frequency sounds are a lower pitch. And we're going to spend a good bit of time, a couple days, talking specifically about sound and looking at some examples and making some measurements and doing some labs. When we're talking about the electromagnetic spectrum, we're talking about the type of light. And so the shorter wavelengths are also higher energy, and that's our gamma radiation. Our visible light is right there in the middle. You see that. And then our longest electromagnetic radiation is our radio waves. They tend to be in the meters. Our gamma radiation is like in the 10 to the negative 9th, nanometers and smaller, picometers. Our radio waves are like 10, 15 meters sometimes for our AM stations. Also similar to when we talked about our circular motion, there's an inverse relationship between frequency and period. And so our frequency is 1 over the period, and our period is 1 over the frequency. If we have an object that oscillates 5 times per second, then the frequency is 1 over 5, or 1/5 hertz. If it's 10 times per second, if it's 10 times per second, then the frequency is 10 hertz, and the period is 0.1 seconds. Okay? As the wave moves through with some frequency, with some period, with some wavelength, using that information we can calculate what's called the wave speed. Speed of the wave, pretty straightforward. Again, as a reminder though, and as I said, we're going to say this 6, 7, 8, 9, 10 times, however many times it takes. Let's see, what are we going to do with this time? Let's try that. I don't like that one. Let's do that one. Waves carry energy with no net movement of matter. That just blocked it out. There we go. Waves carry energy with no net movement of matter. Okay, The matter does not leave. It's only the energy that goes, that changes positions. So when we measure the wave speed, when we're talking about the speed of the wave through a medium or through a vacuum, what we're really talking about is how fast, how quickly is that energy transferred from one place to another. And we can find that if we know the frequency and the wavelength. Because as we remember from our kinematics, velocity is equal to displacement over time. Okay? When we talk about displacements relative to waves, that distance we're talking about is really wavelength. Okay, so distance is our wavelength, and the time that we're referring to when we talk about waves is called the period. So we can think about our velocity as wavelength over period. Okay. Well, we also know, though, that there's that inverse relationship between period and frequency, and so the period is equal to 1 over the frequency. Or we can also say the frequency is 1 over the period. And this, lambda over t, is equivalent to 1 over t times lambda. And we know that 1 over t, as we just said, is equal to frequency. And so we can rewrite this equation as you see it down here. We'll write it a little bit bigger, a little bit brighter. V equals lambda, or wavelength, times frequency. Okay? So if we know the frequency, if we know the wavelength of a wave, we can calculate the speed of the wave. What this should tell you, or what you can see from this, is that the two things that affect the velocity of a wave, the speed of a wave, are the wavelength and the frequency. What happens, what we end up actually seeing, is that as one goes up, the other goes down, because the velocity of a wave is ultimately determined by the medium, the thing that it's moving through, and the properties of that medium. And so the speed of waves in water are determined only by the type of water. Is it salt water? Is it fresh water? What's mixed in? The speed of light is determined by what it's moving through. If it's moving through a vacuum is nothing, right? And so light moves through a vacuum as fast as it does anywhere else. Does anybody know what the speed of light is?
It starts with a 3, right?
If you round up, sure.
And a lot of zeros.
There are a lot of zeros. 2.99 times 10 to the 8th meters per second. Sometimes we'll see that rounded up to 3 times 10 to the 8th, and that's fine. What are a couple of decimals at this point? But it's very, 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 very fast. Now, we compare that to the speed of sound, which is down here. The speed of sound in air at 0 degrees Celsius is 331 meters per second. Now, sound moves faster through warmer air, and the speed increases by about 0.6 meters per second for every degree, which at 20 degrees Celsius, that works out to a whopping 343 meters per second. Okay? Now, contrast that to the speed of light, and this is why we see thunder before we hear it. This is why there can be such a long gap between seeing, we don't actually see thunder, between seeing lightning and hearing the thunder that's associated with it. And it's, how do you tell how far thunder and lightning are away?
1,000.
Count to 1,000, and what if I count to 3 Mississippi, or 3,000? How many is that?
About 3 miles.
About 3 miles, okay? It's a really rough estimate, but it comes from the fact that the speed of light is about 343 meters per second, and if you count that, the time it takes, that 3 seconds, it's kind of 3 miles-ish, depending on how fast you count. I've never actually compared it to real data, but I assume it's close-ish, somewhere between 1 in 17 miles. So the reason for that, though, is because the speed of sound is so much slower than the speed of light. Orders of magnitude slower, clearly. That 2.99 is also kind of the universal speed limit. It is the fastest that light can go in a vacuum, which means it's the fastest that light can go anywhere. It's also the fastest that anything anywhere ever can go. And we get into a lot of relativity and things like that show that. But nothing can ever travel faster than the speed of light. And the speed of light is 2.99 times 10 to the 8th. Now, we call it the speed of light, but it's really the speed of electromagnetic radiation. Because it's not just light, but it's also microwave, it's also X-rays, it's also gamma rays, it's also infrared radiation, it's also radio waves. So the radio waves, whether it's your AM, FM, or your Sirius XM traveling from the satellite up in space, those are traveling 2.99 times 10 to the 8th meters per second from transmitter to receiver. And that's all determined, again, by the medium. And so when light enters a new medium like water or crystal or glass or something like that, it's going to slow down. When sound travels through water, well, it actually travels much faster through water. It travels over 1,000 meters per second through water. It travels over 3,000 meters per second through steel. And that's because of the density, because those molecules, as we talked about when we talked about solids, liquids, and gases, those molecules are packed in more tightly together so they don't have to travel as far and the energy gets transferred faster. Okay? So again, here we have our V equals F lambda. Again, as we've mentioned, the velocity is dependent on the medium. So that means that the velocity is constant in a given medium. In a particular medium. So then in a medium, if the frequency goes up, what's going to happen to the wavelength? So we have electromagnetic radiation. If our frequency goes up, in order for the velocity to stay the same, what has to happen to the wavelength? Has to go down, yeah. And vice versa. If the frequency goes down, the wavelength has to go up. When we look at the magnitudes of our electromagnetic spectrum, our visible light is in the hundreds of nanometers. So 570 nanometers roughly is yellow light. 380 nanometers is purple light. What's nano? What is that prefix? -9. Nano means 9. Nano 9. That one's a. If you can remember those two things, it should be easy to remember. Nano means 9. So 450 times 10 to the negative 9th, which is 4.5 times 10 to the negative 7th meters. Okay. When we get to gamma, now we're getting into like 10 to the negative 9th, 10 to the negative 10th, 10 to the negative 11th meters for our wavelength, which means our frequencies now are very, very, very high. And so just as small as our, in magnitude, are our wavelengths, our frequencies then are that much higher. Okay, so low frequency means high wavelength, high frequency means low wavelength. Hey, questions on any of this? I know we went through a lot today.